same day, different video. In fact, it's mostly a different subject. It's called least squares interpolation, and this is for people who watched my linearizing data guide, where you learn how to linearize data. I did leave one main piece of information out, which is how computers actually do it. And if you don't know, this is what this is for. Caution, it's a Calc 3 subject. It's a Calc 3 topic, and it requires optimization, which I know none of you guys like. At least a lot of people that I know hated optimization. So just warning you. But this is 3D optimization, so buckle up and we're gonna do it. So when we're talking about least squares interpolation, that means we're just trying to approximate a best fit line along a graph with given data points. So for example, if I see a graph looking like, I need a new marker, geez. Right, if I look at a graph like this, right? And then there's data points like this, right? I can draw a best fit line like that, right? Now this is math, this is physics or chemistry or biology or this is science, and we do not care if they're actually on the same line because human error exists. We're not mathematicians. We don't care if there's a single decimal point wrong. If there is a pattern, there is a relationship. That's how science works. So that being said, how do we find a constant for such relationship? Or how do we find this line that is in form of y equals ax plus b, where a and b are constants, right? How do we find such a thing? Well, that's where least squares interpolation comes from. Basically, let's figure out what makes a line the best. And in my definition, or at least a lot of people's definition, the best line is where you choose two constants, a and b, and the total error is the smallest. You're hearing optimization, right? So essentially, the deviation from points from the expected values and actual values, right? Given an equation y equals ax plus b, needs to be at minimum to find the best suited equation. So, okay, well, we have a bunch of error now. Way to represent error. So how do we find the total error of a function? Well, what we can do is we can add up all the errors that you have. For example, if I'm 1 off on this point, and then 2 off, and then 1 off again, and then 5 off, and then 6 off, that's 9 plus 6, that is 15. That's an error points of 15, if we say the total error is 15 off. We want to make sure that number 15 that we got is at its minimum, because we're adding up all the errors of the data points. So let's make a function. Let's call it error function, right? And no, it isn't like that. I think from the stat where you do the exponential error function for normal distribution. No, this is different. This is just something I'm naming it. Error. Right, let's write it over here. Error of a comma b, because those are the two constants, right? Right? Now we want a way to give. Now we also keep in mind we're given data points of one independent variable x, x1, x2, xn, comma y1. The dependent data points y1, y2, yn, right? So we have these data points, right? And we want to basically add up the deviation of x1 and y1 from its expected values. Basically, we want to sum. So let's sum that. Sum where I equals 1 to n, because we have n data points. Sorry for the sigma sign looking weird, bear with me. And the deviation is going to be yi, which is basically, yi means basically the yth data point, which is basically y1, y2, y3, y4 until yn, right? Now we're gonna have to subtract it from its expected value, which is a times x1 plus b, a times x1 plus b, because that's expected. Now we also make sure, because this could be negative, and if we have a negative, that's bad because we can actually reduce the error value, right? Because if this is 1 and this is negative 2, our error value is technically 1, but that's in reality 3 because you're, 3 away. So let's do this. It doesn't matter if it's the real error value, we just want to minimize it. So let's just square it. So if we square out every negative number, it becomes positive, and we don't have to worry about that. So yeah, now we want to find the absolute minimum of this function right here. And if you couldn't realize it already, this is basically going to look like a quadratic on the plane. So it's going to look like an ice cream cone. No, like I don't know how to describe it. Like a cone like that, and the minimum is going to be like the tip of the cone, right? It's going to look like imagine take a paper and put your fist to it. It's going to look like that. The paper shape is going to look like that, and the minimum is going to be where that's at its lowest. The fist parcel is going to be around here when you have the paper. So yeah, well, this is where the 3D optimization is going to come in. We want, if you haven't noticed, when it's at its minimum, both its change in y and its change in x with respect to the error value, which is the z-axis, are both 0. Which means we want both partials to equal 0 for the same b and a. So what that means is we're going to have a system too. I think it's going to be linear, so don't worry about it. So yeah, let's do this. So let's take two partials now. Partial, oh my god, partial e over partial a. So now we're taking a derivative of the partial derivative of a with respect to, e with respect to a. So remember, this is we're adding up a bunch of values, so we can just do them separately. We can treat yi and xi like constants because they actually are too. This is xi, my bad. So let's do this. So chain rule first. So we have this sum stays, right? Because it's just a sum, doesn't matter. We're just doing each term individually. 2, because it's chain rule, times derivative of that is, so we have, I'm just kind of blanking out. yi minus axi plus b, because it's chain rule, right? Minus b actually. Yeah, minus b. Now we gotta do another chain rule because negative xi is technically a constant, so let's multiply by negative xi. Right? Now partial e with respect to partial b, that is going to equal the same thing. We're going to have a sum again. I equals 1 to n, right? Another chain rule, so there's going to be a 2, right? Same thing, we're going to copy it down. We're basically distributing the negative over here, so minus axi minus b, and in chain rule there's a negative here, so times negative 1. So yeah, now we want to make sure they're both equal to 0. And now we have these two values are not squared, so we can actually have a linear system, which is really good. We learned to solve those in the 8th grade. We're fine. Let's factor our 2. That's what we're technically doing, and then divide it so 2's go away essentially. And let's multiply everything inside. So we're gonna get, let's write it over here actually. 0 equals, this one is gonna be negative xi. Also, let's do one more thing. After we distribute it, I'm gonna break the sum apart, right? Because you can do that. It's really we're just adding up terms. We're just really grouping them if you think about it like that. So 0 equals the sum of I equals 1 to n of negative xi yi. Then we're going to multiply this and that. So we're going to have plus some I equals 1 to n of xi squared, and the a can go on the outside, but it doesn't matter. So let's just put the a there. And then that's going to be another plus some I goes to 1 to n of xi b. Yeah. So now we have another equation too. 2 goes away, so let's multiply it again. Negative 1 times yi, that's going to be sum of I goes from 1 to n of negative yi, right? We're going to have a negative go on that side, so it's going to be plus sum of I goes to 1 to n, and then we're going to have a xi, right? No, that, and then the a is just there. The a is just there. Remember, a is the variable. Xi, yi, these sums are just constants, right? We're making a formula. So, and then negative 1 times negative b is b, and we're adding b with itself n times. Let's go back to the 3rd grade. If you're adding a number, it's by itself a certain amount of times. You're multiplying. So that's just going to be bn, right? So now let's add this on that side, this on that side, because it's a negative. You know, make it neat, no negatives. So let's rewrite the equation when my marker decides to cooperate. Bn. So yeah, this is a linear system because I know it's gonna be a pretty scary looking one because they're really like no numbers, but this is something you learned to solve in the 8th grade. Nothing scary. This is one variable, one variable, one variable, one variable. You just have to you can use determinants and matrices, or you can use like standard substitution or elimination. But this is a linear system and you can solve it really easily. And on top of that, computers are really good at this type of stuff. So yeah, this is how you find the best possible a value and b value for this equation to find the best line. Yeah, thank you.